Welcome back. We're continuing our very first chapter, reviewing linear modeling. That's just word problems for linear graphs. Many of our real world situations that we encounter in these word problems can be modeled by linear functions because they involve a constant rate of change. Remember, another word for rate of change is slope. Every time you take a trip in a car at a constant speed, the distance traveled is a linear function of the time given. Remember also that independent variables are the ones where we control what we put into them. It's usually x. And dependent variables are the result of plugging in our chosen value. So the answer is another way to say that. The answer depends on what we put in. This is typically going to be y. So let's try a couple of these. We have a car traveling at a constant speed of 70 miles per hour. So distance is 70 times t, the time, in hours. We could also say that that is y equals 70x, if that helps. That means that our slope is 70 or 70 over 1. So we travel 70 miles for every 1 hour on the road. Our y-intercept, let's change to this. Our y-intercept, that's not very easy to see, is 0 because we don't have the plus b added here. So if I don't have anything there, then we say our y-intercept is 0. So this means at the start of our trip, we have traveled 0 miles, which makes sense. If we haven't left yet, then we can't have traveled anywhere. Also wants the independent and dependent variable. So the independent variable is time because we are choosing the amount of time that we're going to travel. And then the dependent variable will be the distance traveled because the distance we travel depends on the amount of time we choose to stay in our vehicle. If we fill out our table of values, remember we're doing distance as a function of time is equal to 70 times time. That means we're plugging in these values for t. And we start with 70 times 0, which is 70. 70 times 1. Oops, sorry. Did I just say 70 times 0 is 70? I apologize. 70 times 0 is 0. So we haven't traveled anywhere. 70 times 1 is 70. 70 times 2 is 140. 70 times 3 is 210. Times 4 is 280. Times 5 is 350. And times 6 is 420. And remember, all of this is miles. Now, if we graph that, Okay, we not only have our graph here, but we have to make sure we label and scale our axes. What that means is our y is distance traveled in miles. And I am going to have this go by 70s. So starting here in the corner at 0, 0, 70, 140, 210, 280, 350, 420, 490, and so on. Remember, you can make the scale anything you want. I just chose to go by 70s, make it a little easier on ourselves. And then this is our x-axis. And we will make this hours. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on for the hours. And remember, you probably want to have a straight edge to be able to connect your dots. Looking at the table we just made, we have 0, 0, 170, 2, 140, 3, 210, and all the way up here to 6 hours. We can't have this line have arrows going both ways because we cannot have negative time or negative distance traveled. So we're starting at that 0, and we can have an arrow going that way because we can travel unlimited hours for an unlimited amount of distance. Now, does it make sense that we're going to travel for 50 hours in one shot? Probably not. Not unless we have a lot of people that are able to drive so people can sleep. Use that model to find the distance traveled after 3.25 hours or 3.25 hours. And so we're still using this. We're plugging in 3.25 for t. And so in my calculator or in my head, whichever way you want to go, 70 times 3.25 is going to be 227.50 miles. That's not too bad. Our destination is 595 miles away. How much driving time will it take you to reach your destination? This is not including stops. So now that we know that our distance is 595. So 595 is equal to 70t. It asks you to find out how much time. How much time? The opposite of multiplying by 70 is dividing by 70. And we have 8.5 hours is equal to the time. And then we can always go on our graph for letter F to check and make sure that the answers that we got are reasonable. So if I go back to 595, it's going to be, let's see, this would be 560, and then 630. So we're roughly about right here. And yeah, a little over 8 hours, 8.5 hours, that works. And then 3.25 hours is roughly about right here. So yeah, I think that 227 looks pretty reasonable as well. All right, let's move on to example 3. We have a population of fish. We're trying to create a function. And so you can take any 2 ordered pairs you want. Okay, these are ordered pairs. The year is probably going to be our x, and the population in fish is y. Time is usually our independent variable because we can choose how much time we're going to allow to pass. And so I'm just going to go ahead and use these first two, actually, to find my slope. So I'm going to start with 238 minus 237 over 2,000 minus 1995. So that gives me 1/5. Remember, this one is really 1,000. So we're increasing 1,000. I'm going to put this on here. Increasing 1,000 fish every 5 years. 1,000 fish every 5 years. So the only other thing we need is a y-intercept. And so here's what we need to discuss. We have an initial year. The year we first started counting was 1995. And so this is going to be year 0. Year 0. So if year 0, our initial year is 1995, and 1995 was 237,000, then this is going to be our y-intercept. I'm going to have y equals 1/5 x plus 237. But to put it in terms of this, we have population and time. So y is now going to be population, and x will be t for time. So 1,000 for every 5 years. Using this model to predict the population of fish in 2023, well, first I have to figure out, well, how much after 1995 is the year 2023? And that's 28 years. So if I plug that in, the population in 28 years, 1/5 times 28 plus 237 gives us, when we plug it in, 242.6 or 242,600 fish. And you can check that, every 5 years you're gaining 1,000. So we could estimate to see in our table, the year 2020 would be next, and that would be 242. And then 2025 would be 243. So does 242.6 make some sense? If we're in the year 2023, it's a little more than halfway. 2023 is a little more than halfway between 2020 and 2025. So I definitely feel like that works and it makes sense. All right, this is where we're stopping for today. Thanks so much for joining me. Have a great rest of your day.